In this video, I will describe the challenges with just using depth-first search to determine whether or not there is an existing path between two characters in the graph, and how we can approach solving it. First, we have W, R, and T. So at this point, the graph is a glorified linked list. When we insert F, we have an edge between R and F, and so now we're updating it to the graph. Next, we would insert ER, and then the first step, which is fine, is ET and T. We have a valid path between E and then R and then T, which means we already have established the ordering, so therefore we do not need to create an edge. But this word is the first example of when we run into trouble. We have R, F, T, and T. In the naive approach, when we do R and F, we see that this edge already exists, so we're not going to insert a new one. Next, we're going to go F and T. We see that there is not an edge between F and T, and also if we perform depth-first search, there's no path between these. However, if we were trying to use a way in which we could determine which ordering we want to do between these three particular vertices, we run into a problem. Because we inserted R and T first, before R and F, if I ran a topological sort or a minimum spanning tree, both of those would contain this edge and would eliminate this edge. But that's not what we want. We want a situation in which we can properly evaluate and remove the edge listed here in red. So if there exists a path between these three characters, where we already now know that there's a path from R to F, there's a path from F to T, and in the proof that I wrote up, I called this vertex 1, vertex 2, and vertex 3. I'm sorry, this is vertex 1, vertex 2, and vertex 3. We want to ensure that the path goes in this order. So we see that we can now do a depth-first search from R to T, but we also know that there exists an edge between F and T. So we would use the logic that if there is an edge between vertex 2 and vertex 3, and there's an edge between vertex 1 and vertex 3, then we want to remove the edge between vertex 1 and vertex 3 to get our ordering. So now we're much closer to having an ordered solution. Next, we would insert WER. We already know that there's a path between E and R before we even start going through it. And we know that there's a path between W and R. So we're going to have our three-node problem. First, we would insert W and E. And notice there's a difference between these two, in that before, we already had these two edges and we inserted between the second and third node. But here we're inserting between the first and second node. So when we get to E and R, we see that an edge already exists. But we still want to check whether or not the previous and this value exists. So if there exists an edge, we have vertices V1, V2, and V3. And there's edges between V1 and V2, V2 and V3, and V1 and V3. In order to get this proper ordering, we want to remove the edge between V1 and V3. At this point, we now have the alphabetical order for all of the words that have been inserted to this point. The crucial aspect is the adjacency list ordering is not the ordering that we eventually want. See, we have W, E, R, F, and T, and we just iterated through. We have vertex 0, 1, 2, 3, and 4, which gives us W, R, T, E, and F. This is another example of understanding the difference between data and structure. So how would we actually produce the final solution here? Well, we would start at the origin, and then we would do a sorting. A topological sort will work perfectly here. WE, E then goes here, E now goes to R goes to F, and then F goes to T, and T is where we terminate. So this ordering produces W, E, R, T, W, E, R, F, and then T, which is the exact ordering that's represented at the algorithmic level.